Next, okay, we are going to look at the exercise 4J question 5. We have a rectangular pulse ET is applied to the RC circuit. So this is a resistor, this is an inductor. R is 10 to the power 6 ohm, C is 1 microfarad. Okay, as shown in figure Q5, show that the circuit can be modeled as RC dV dt plus V equal to HT minus HT minus 2. Okay, first of all, okay, we look at the ET given by the left hand side figure here. So Laplace transform is for positive t. So we look at the positive side. So the ET equal to 1 when t from 0 but less than 2. Okay, when t greater than 2, the voltage, the ET become 0. That's for t greater and equal to 2. Okay, this is step function. Then we convert to unit step function. Remember, factor out the top function, which is 1. Okay, and then takes the bottom, deduct top, which is 0 minus 1. So we take 0 minus 1. Okay, the discontinuity point is t minus 2. So multiply by ht minus 2. So you got 1 minus ht minus 2. Okay, 1 is actually ht. So ht minus ht minus 2. Because we have seen Laplace transform for 1 is 1 over s, ht is 1 over s2. Okay, and then we got the RC circuit. So voltage across R, VR, plus voltage across capacitor VC is equal to ET that we have found, which is HT minus HT minus 2. Okay, they want to show, to find the voltage across capacitor denote as V, V here. So mean we want to find the voltage across capacitor, which is denote as V. So we know VR is IR. So VC is denoted as V. So equal to HT that we have found. ET is HT minus HT minus 2. Okay. The current flows through the resistor is the same as flow through the capacitor. Okay. And we know that VC is actually VC or equal to V is actually 1 over C integral I dt. Okay, mean I here, I flowing through resistor and capacitor are the same. Okay, so you want to solve, we want to solve for I. So you can have C times V equal to the integral I dt. To get I with ddt both hand side, where C is constant, that's why I got C dV dt equal to your ddt integral I dt. So you have C dV dt equal to I. When the dtt meet with integral dt, we get back I. So that's why I here is actually C dV dt. That's why you got R C dV dt plus V equal to HT minus HT minus 2. Okay, and then plug in. Okay, R is 10 to the power 6. C is 1 micro F, which is 10 to the power negative 6. So R times C, you have 1. Okay, in here. Okay, this one, still the exercise 4J question 5. So R is 10 to the power of 6. C is 10 to the power negative 6. And then dV dt plus V equal to HT minus HT minus 2. Okay, so you got dV dt plus V equal to HT minus HT minus 2. Okay, then we take the Laplace transform at both hand side. Okay, we're taking the Laplace transform So dv dt plus v equal to the Laplace transform for ht, okay, minus ht minus 2. So Laplace transform for dv dt, we have s vs minus v0. So Laplace transform for v will be vs. Laplace transform for ht is 1 over s. Laplace transform for ht minus 2 is exponent negative 2s over s. Okay, let me check back. Okay, the table Laplace transform. Okay, vt, so it's a vs. dv dt, so s vs minus v0. ht minus a exponent negative as over s. Okay, so the first step, taking Laplace transform. Second step, substitute, okay, initial condition. Okay, back here. Calculate the response Vt with V0 equal to 0 using Laplace transform. Okay, given V0 equal to 0. Then we have S Vs, because V0 equal to 0. So plus Vs equal to 1 over S minus exponent negative 2S over S. Okay, the third step, solve for Vs. So factor out Vs at the left hand side. So first term we got 1 at S. Okay, second term 1. The term without Vs we bring to right hand side. So 1 over S. Okay, we can go like here. Minus exponent negative 2S. So that's why Vs is actually, okay, 1 over S over S plus 1. Yeah. Okay, the fourth step, taking the inverse Laplace. Okay, fourth step, taking, okay, inverse Laplace. So we get back Vt, which is the inverse Laplace of Vs. Okay, we have the inverse Laplace of, okay, we break it, 1 over S over S plus 1. So minus the inverse Laplace of x minus exponent negative 2S over S plus 1. Okay. And then, okay, in the question 4 just now, we have shown that the inverse Laplace of 1 over, okay, this one, and we solve for the also the charge Q. Okay, the inverse Laplace of 1 over S plus 1 we obtain is 1 minus exponent t. This one. By using okay, the inverse Laplace of 1 over S plus 1 by using okay, this one, using the transform of integral, or you may use a partial fraction. So you have in the form of inverse Laplace of Fs over S. Okay, by using transform of integral will be the, okay, integral of f tau d tau from 0 to t. So Fs is 1 over S plus 1. So Ft is exponent negative t. F tau is exponent negative tau. So integrate exponent negative tau, where the tau, okay, from 0 to t, we get, okay, negative exponent negative tau. Okay, limit from 0 to t, plug in t into tau, so exponent negative t. When plug in lower limit with 0, so minus exponent 0 is 1. So we get 1 minus exponent negative t. Okay, hence, okay, this one by using transform of integral here, the inverse Laplace of Fs over S, the result is the integral of f tau d tau from 0 to t. Okay, we obtain the answer from question 4. This is 1 minus exponent negative t. Okay, and this one by using the second shift property, because by using the second shift property, okay, this is in the form of inverse Laplace of exponent negative 2s fs. Okay, the result is ft minus 2 ht minus 2. Okay, where it's the same fs 1 over s plus 1. So your ft is here. So ft minus 2 will be 1 minus, mean the t here, you change it to t minus 2. So ht minus 2. Okay, check the question number 5. Oh, yeah. Yeah. So the Vt is 1 minus exponent negative t. Oh, because here, so minus, okay, minus 1 time ht minus 2 plus, okay, exponent negative t minus 2 ht minus 2.